The following is a video of the Brookhaven Power Transmission Project. Electrical engineer, Eric Forsyth acted as project manager and has preserved this video of this historic project. In the early 70s, President Nixon asked the National Science Foundation to fund research that was relevant to the needs of the country, not esoteric research few people could understand. The program was called Research Applied to National Needs, run. Brookhaven National Laboratory submitted a proposal to investigate the use of superconductors for large-scale electric power transmission. The laboratory had some expertise in the design of superconducting magnets which, if successful, could lead to a type of particle accelerator which was not possible with conventional copper-wound magnets. Brookhaven received some funding and spent a year examining possible technical solutions and visiting other institutions which were working on the problem, including some in England, France, Austria, and Germany. Brookhaven proposed a hands-on project to demonstrate the technical feasibility of the approach and were funded to develop suitable materials and then build a prototype demonstration on a scale of interest to electric utility companies. They chose 138 kilovolts, 3-phase, as the operating voltage and a transmission power rating of 1000 megavolt amps. In this movie, you will see early, small-scale laboratory experiments to measure the characteristics of various materials under consideration for the insulation and conductor designs. Next, was the construction of a test site, and in 1982 the first trials of cables about 100 yards long, rated to carry 4000 amps at 60 Hz was conducted. This was the first time superconducting cables designed for power transmission had carried rated current and voltage simultaneously. The system was operated on 9 occasions over the next 4 years, testing the cables for overcurrent, overvoltage, and simulating many of the faults that might occur in electric utility service. This movie shows a test run in 1985 when the system was powered to 50% overload or 1500 MVA, for over an hour. There was intense disappointment when, in 1986, funding was dropped for the project by the Department of Energy. The merit of this work was recognized by the Institution of Electrical and Electronic Engineers, IEEE, in 2007 when, as project manager, Eric Forsyth was presented with the Herman Halpern Award, the highest award given annually for power transmission research. The citation reads for the practical application of superconductors to power transmission technology.
In the United States, underground transmission lines comprise only about 1% of the network which moves bulk electric power from generators to user or from one utility company to another. The relatively low installation cost has led to the overwhelming use of overhead lines. In addition, technical problems limit the useful length of underground cables to about 20 miles compared to the many hundreds of miles possible with overhead lines. As older and smaller generators in downtown locations are replaced by larger generating stations situated outside urban areas, the need arises for transmission facilities through the surrounding suburbs back to the load center. Due to lack of space for the right-of-way needed for high-voltage overhead lines, or simply for aesthetic reasons, there is pressure to place as much of this new transmission as possible underground. In the early 1970s, engineers at Brookhaven National Laboratory pointed out that the use of superconducting cables would largely eliminate the limitation on length associated with conventional underground cables, and at the same time provide very high circuit power capacity in a relatively small diameter pipe with minimal impact on the environment. Virtually none of the technology existed at that time, and the first step was to develop suitable materials. Superconductors are compounds of niobium which can carry very large electric currents when cooled to temperatures near absolute zero. Here, a short sample of superconductor under development at Brookhaven is being evaluated by placing a small length of cable in a dewar full of liquid helium, which cools the superconductor down to 4 degrees above absolute zero. Laboratory tests to evaluate new materials were an essential step before making longer cables, which eventually achieved a maximum length of about 60 feet during this phase of the development program. The electrical insulation being applied by these machines is another cable component which required extensive development. Cables in lengths of several thousand feet are transported on large reels. A major problem was to develop an insulating material which would not be damaged by the process of reeling and unreeling the cable. After a bend test in the laboratory, the cable is dissected and inspected for damage to the electrical insulation. Later on, these tests were speeded up by the development of a non-destructive X-ray method at Brookhaven. During the course of the project, the Anaconda Cable Company sold off some of its production equipment. The modern machines were snapped up by other manufacturers, but Brookhaven was able to acquire an old taping machine first installed in the Anaconda factory in 1907. Although its low production rate made it uneconomic in the 1970s, it was an ideal tool for the construction of prototype cables needed for speedy evaluation of developmental conductor and insulation in the laboratory. However, before it could be used, the machine had to be completely stripped, cleaned, and refurbished. Within a year of delivery at Brookhaven, 4 sections of the machine were set up and were ready to make new cables. The equipment is housed in a special clean room which minimizes contamination of the cables during construction. Here, the first of many short prototype cables is running through the newly installed taping line. In all, a total of 7 superconducting cables were made before enough knowledge had been gained to attempt the construction of a 1,000-foot cable, a development phase that lasted about 4 years. In 1975, construction was started of an outdoor test facility so that cables could be tested on a scale comparable to an actual utility company application. The site would provide all the necessary electrical excitation equipment and refrigeration needed for full power tests of cables about 350 feet long. Construction of the facility and installation of cryogenic equipment went on in parallel with cable development. The control room for the site was to be located in an old building moved from elsewhere in the laboratory after its original purpose had been fulfilled. It was placed on concrete block walls to provide a 2-story structure. The cables are cooled by a large helium refrigerator, seen here being rigged into the equipment room at the test facility. Helium is the only practical coolant for superconductors. In this installation, the refrigerator provides cold helium gas with a pressure of 225 pounds per square inch and at a temperature of about 7 degrees above absolute zero. In 1981, the first cable intended for the outdoor test facility was fabricated on the taping machine. It has a rating of 138,000 volts at 4,100 amps, or a three-phase rating of 1,000 megavolt amps, MVA, per circuit, and was made in one length of about 1,000 feet. 1,000 MVA circuit is enough power for a city of about 1 million inhabitants. To put it another way, 1,000 MVA is about 1/8 of the maximum power ever required by New York City on a hot August afternoon when all the air conditioners are running full blast. It is very satisfying to note that the old taping machine, which for over 50 years made many thousands of miles of transmission cable lying under the streets of American cities, is now producing the most advanced power transmission cable ever made. All materials loaded on the taping machine which go to form the cable were made commercially under subcontracts from Brookhaven. The superconductor itself is in the form of a thin tape only 5/1000ths of an inch thick, which was made by the Intermagnetics General Corporation of Schenectady, New York. The insulating tape is slit from sheets of high-strength polypropylene made by the Bryce Corporation of Memphis, Tennessee. During fabrication, the cable made 12 passes through the taping line before all the layers were in place. After completion, the superconducting cable was moved on a reel to the outdoor test facility a few hundred yards away. By this time, the cryogenic equipment at the facility had been installed and checked out. It would not be run again until the cable installation was finished. The white pipe seen at the test facility is the cable enclosure. Normally, this would be underground, but at the test facility it is placed about 3 feet above the ground for easy accessibility. This pipe itself was the subject of several years' development in order to optimize the cost and thermal performance. The outside of the pipe is at ambient temperature, but inside, the cable is operating at a temperature of only 7 degrees or so above absolute zero. The pipe is made in sections of about 60 feet. 5 sections are welded together here to form a total installation length of a little over 300 feet. A significant technical breakthrough made during the development of the enclosure was to maintain a vacuum in the pipe without the use of pumps. When the cables were finally tested, the vacuum had remained for over 5 years. With the reel in position, the cable was pulled into the enclosure pipe in 2 operations.
He's got to pull it. You want that cat there to be pretty tight.
First, about 400 feet was drawn into the pipe and the cable was cut. Then a second cable was drawn in, thus allowing a circuit to be made with 2 cables, each about 400 feet long, before final trimming.
Must have a certain
Connie, try not to.
kind of sound on this one. Going back and forth. Gone.
Gone. Bye.
There it is.
This installation simulates the actual pulling operation that would be used in a utility cable system. Possibly conditions were too realistic. A steady drizzle developed, which persisted throughout the morning and the afternoon needed to complete the pulling operation. With conventional cables, there is a heavy center conductor to take the strain of pulling the cable down the pipe. In the supraconducting cable, all the components are relatively fragile, and stainless steel outer armor tapes were provided, which are welded to the pulling head to take the pull force of about 400 pounds. However, this was the first time such an operation had been tried, and there was a good deal of relief when the cable emerged at the far end of the pipe without suffering visible damage.
Here it is. Here it comes. Hip, hip! I have to ask a question, Tom. Come through. Who slows down first, Tom?
We do what I tell him.
Okay. We do. He'll tell you when. You slow down first.
After the cables had been installed, the last major task was started. The installation of the 4 terminations, one at each end of each cable, which provide the connection from the cold cable at one end to the ambient temperature electrical circuits on the outside. Technicians are placing blankets of super insulation on the pressure vessel of a termination. This illustrates a technique of cryogenic engineering which minimizes heat inleak to the cold parts of the system. Super insulation consists of multiple layers of aluminized plastic which prevent radiation from the warm exterior to the cold interior. The ends of the superconducting cables had to be prepared to match the joint to the electrical components of the termination. The electrical insulation is carefully made into a predetermined shape by the hand application of additional insulating tapes. Metal strips which carry the current when the cable is cold are also carefully shaped and trimmed to the correct length. The superconducting cable has both inner and outer conductors, which are designed to carry equal currents but in opposite directions. Each conductor consists of 4 layers of tape, a pair of superconducting tapes and a pair of copper tapes. Copper tapes are provided to carry current if for some reason the superconducting tapes pass out of the superconducting regime. This can happen, for example, when the network is accidentally short-circuited and very heavy currents, perhaps 10 times the normal value, may flow briefly. A completed cable end awaits the next step in the assembly of the termination. The termination design posed a challenging problem. It must carry the same voltage and current as the cable themselves, but at the same time operate with a temperature difference between one end and the other of about 540 degrees Fahrenheit. The component of the termination which actually crosses the temperature transition region is known as the cryogenic bushing, and here the connection is being completed between the bushing and the inner conductor of the superconducting cable. Small adapting pieces are fitted to connect the conductors of the termination to the prepared ends of superconducting cables. When the electrical connections are completed, a large cylinder slides over the assembly, which contains the high-pressure helium gas used to cool both the cables and the terminations. The cold helium gas from the refrigerator is introduced into the system at the west terminations. Most of the gas flows to the east end, but a small percentage is used to cool the termination conductors. With insulation in place and everything leak tight, the termination needs only the outer vacuum tank to complete the cryogenic section of the assembly. This portion of the termination is sealed by the flange, which makes the connection between the various high-pressure components of the termination and the vacuum containment vessel. Careful adjustment is necessary after assembly to ensure that the joints are vacuum tight. After a last check for leaks, more super insulation is added. The vacuum containment vessel, which is the outside surface of the termination, permits the air to be evacuated from the space containing the super insulation blanket. Once the air has been removed, heat can no longer penetrate to the interior surfaces by means of convection. The vacuum space of the cable enclosure pipe seen earlier is permanent and does not require pumping. However, due to the large number of joints and the need to disassemble the terminations on occasions, the vacuum in this part is maintained by the continuous operation of pumps. As the termination assemblies neared completion, work started on the electrical bus bars which connect the terminations to the supply equipment. The power supplies provide simultaneous voltage and current at the correct level to energize the cables to the maximum rating of the system. Although the cables will carry a great deal of power, it is not actually used or turned into heat. Power is simply transmitted on a round trip to one end of the cable enclosure and back, and then returned to the electrical supply network feeding Brookhaven Laboratory. Although in an actual system, 3 cables would be used in a 3-phase system, the tests performed at Brookhaven use 2 cables in a single-phase circuit. Each cable will carry a rated power of 333 MVA. corresponding to 1,000 MVA on a three-phase basis. Here, the copper bus bars which connect the power supplies to the west end terminations are being lifted into position on the insulated supporting stands. The size and weight of the bus bars, which carry the same current as the supraconducting cables, emphasize the amazing current carrying ability of supraconductors. The bus bars have a cross-sectional area about 400 times larger than the supraconducting tapes forming the cable conductor. These were seen earlier as the thin metal strips which were formed to complete the cable ends.
Got enough bolts up there?
With assembly complete at the test facility, preparations begin for the initial cool-down and electrical testing. First, the compressor must be started and the refrigerator operated for about 4 days before the cables become cold enough to energize. The refrigerator operates on the same principle as the everyday kitchen refrigerator. Gas is compressed and the heat of compression removed. When the gas is expanded, it cools down. The refrigerator at the test facility has a 350 horsepower compressor, and the helium gas is expanded by 4 turbines, turning at speeds of up to 186,000 revolutions a minute. Final adjustments are made to the cryogenic system, and cooling gas starts to flow in the termination conductors. In the control room, preparations begin to apply voltage and current. Operation of this complex equipment is facilitated by the extensive use of computers, which monitor conditions throughout the test system and display the results on TV screens. Conditions throughout the system are also printed on paper and stored on magnetic disks for review later. Control room personnel are presented with a computer simulation on which the operating conditions of each part of the system are displayed. The display is color-coded in order to let operators know which valves are open and which are shut.
Interlocks are all satisfied. Okay, we're ready for high voltage. You want to clear the area, Rich?
High voltage is going on.
High voltage on.
High voltage is applied first and the cable performance checked up to the rated level of 80,000 volts, single phase.
Now up to 50 kV, 60. Okay, we got voltage on the line. 80 kV, 80.4 as a reading. Partial discharge, no change. Okay, check the partial discharge on the storage scope bridge.
Performance looks good, so current is applied at the same time as voltage. Slowly, the level is raised to 4100 amps, corresponding to 333 MVA on each cable, or 1000 MVA three-phase, the design goal for continuous steady-state operation of the superconducting cables.
Now at rated current. Cable on balance is 26 amps falling. Amps, 19. Okay, that's good enough. We've got 7 amps of unbalance, 4,050 amps cable current, which if you could log that.
After verification of performance at 333 MVA per cable, the power level is raised. The cables are designed to run at 500 MVA for 30 minutes, a condition corresponding to emergency levels on the network. The extremely high reliability of the U.S. electrical transmission network is in part due to the ability of all components to carry extended overloads, so that faults do not cause a chain reaction failure or blackout of the whole network.
It's emergency power rating, 6,000 amps. This is the emergency power rating, 500 MVA.
Successful operation of the Brookhaven test facility, which is by far the largest such facility in the world, has demonstrated the technical feasibility of carrying very large amounts of power in underground superconducting cables. This is still a long way from installing and operating such a system in an actual utility network. Brookhaven is now planning the development needed for the next phase of implementation of this technology into the power delivery system of the U.S.